Hi, my name is Jacob Domingues, and this is Lab 4 Oscillations. So, first of all, this lab is a comparison between a computational model and an experimental model of a system spring, or a spring mass system, which is just a mass attached to a spring, moving against gravity, so vertically up and down. The ability for this lab to work is thanks to these important principles of physics, which is Newton's second law, the energy principle as well, which we'll go into more later, as well as period of oscillation for a spring mass system, which has its own unique function. Analysis of initial conditions as well as calculations of other factors will allow us to create a semi-accurate model to represent our experiment, and this will also allow for easy calculations of energy at all the different points, and also give us the ability to graph energy throughout our experiment. So here are the models I used. This is the video that I used for the spring system oscillation. It's just a spring mass bouncing up and down. It kind of has an elliptical travel path in total. And yeah, it oscillates due to gravity and spring forces. It's going to keep going over and over and over again. So the next slide here is my tracker, which I used to track the path of the spring mass system. I just, for each frame, went ahead and took a data point, and it converts those data points into numbers in the computer. So for my computational model, I created a model that's intended to accurately represent the experimental form on the previous slide. There was starter code provided to me, but the initial conditions were plugged directly in from the tracker analysis of the physical experiment, and the creation of the computer model will come in handy when graphing the energy, as I said before. Obviously, there will be some slight errors, though, as there are infinitely many tiny forces that could be going against the system and possibly interrupting the perfect imbalance of the two forces, the gravity and the spring. So here's the video of see the energy changes as well as the position and time changes. And then we can go ahead and go to the next slide. So this is the code that, basically all the functional code that I was using for the spring mass system computational model. But these are the important parts. Top left, we have the initial conditions, or the properties of the ball, the kinematic conditions of the ball's mass, the ball's initial position, and the ball's initial velocity, as it wasn't dropped perfectly. As well as the initial calculations that I made down there in the bottom left, gravity of the spring constant, the L naught, as well as the L hat S, and all the different energy initial conditions were all calculated using the mass, position, velocity, as well as some other equations, which we'll go more into later. The motion loop shown on the right is what really makes the computational model function, and it shows it's just a while loop that changes once every frame, which is the same as the video, of course, so it should match up with the video. Here are my results. So the oscillation is seen in the position of the X and Y, and it creates that clear sinusoidal shape, and we'll just go into that more here. Just like the experimental model, the computational model also has that sinusoidal shape, and it's due to the two forces in the system, just being gravity and the spring. One of the best ways to look at this is to look at the actual forces themselves, and we'll go into that here. So first of all, the system is, when we're looking at forces, it's just the mass. When we're looking at the surroundings, in this case, it's best to assume that the Earth and the spring are the surroundings, applying forces to the mass. So these two forces were, again, coded directly into the program. Easy substitution with gravity, Newton's second law, with the spring Hooke's law, which just negative kx. The oscillation that's going on over here. The creation of the sine wave for the position is due to the two forces never being able to balance out. The force of gravity is always going to pull down on that spring, and will always be able to move it down. The spring force will always pull in the direction of the equilibrium position. So sometimes that's up, sometimes that's down. That's what creates that sinusoidal shape. This system will never reach equilibrium, and will continue to go back up and down forever, because it'll be trying to reach that equilibrium position forever, but it won't, because the gravity is pulling on it downwards. So lab questions here. What does it mean that the energy, the what does it mean questions, they're both what does it mean questions. Is the energy principle satisfied? Yes, it is, in this case, because energy principle is just, in this case, if we take the Earth, spring, and mass system, therefore no external work, no external heat transfer, and total energy must equal 0. As you can see in our energy versus time graph over here on the right, there's literally 0 change in delta E, which is perfect, because that proves our energy principle to be satisfied, as there's no energy change, and we're taking the system to be everything, so there shouldn't be an energy change. What is our period of oscillation shown for X and Y? So the one way to calculate the period was just going peak to peak, and looking at it and seeing if they're the same. They were off by 0.001, so basically the same. It makes sense that they're the same as they're traveling on like an elliptical path, and therefore half the travel distance would be the same for x and y. And yeah, that's about it. Thank you so much.